Previously on Chemistry Z, our heroes learned the two secret techniques needed to make ionic compounds conduct electricity. And just when they discovered the meaning behind electrolysis, they were attacked by an onslaught of half equations. But by remembering the words from the ancient witch, our heroes were able to balance these half equations. And now, all of the training that our heroes have undertaken have led to this single moment when they take on the twin gods of Chemistry 1, Endothermic, Exothermic. Will our heroes be able to achieve Ultra Instinct and slay these two monstrosities, or will it be too hard to handle? Find out in this season finale of Chemistry Z. Here's the retrieval grid for this lesson. You know what to do. Anodes are positive electrodes. Cathodes are negative electrodes. Diamond, graphite and silicon dioxide are the three examples of giant covalent structures that you need to know. Halogens are group 7 elements. You calculate moles by dividing the mass by the molar mass. And finally, concentration is calculated by moles over volume. Let's imagine that you've got a hot cup of coffee.
Oh, that's hot. That's hot.
To get you thinking about the conservation of energy, have a go at these challenge questions. Over time, the temperature of the coffee will decrease, and over time, the temperature of the room will increase. Based on the fact that the energy is moving around from one place to another, it doesn't appear out of nowhere or disappear into thin air. This means that energy cannot be created or destroyed. It can only be transferred from one form to another. Now, imagine that this burning piece of coal is the only thing in the universe, and there's 2,000 megajoules of chemical energy stored inside it. Currently, there's 10 megajoules of thermal energy, and finally, there is 1 megajoule of light and sound energy. Here is the challenge question for you. How much total energy was there in the universe before and after the coal has completely burnt up? There was 2011 megajoules of energy both before and after the coal burnt up. Remember that energy is just transferred from one form to another. The amount of energy in the universe stays the same, it's constant. There is just a movement of energy from the system to the surrounding, or from the surrounding to the system. The system is any specific chemical reaction that you're concerned with. We can track the movement of this energy by working out the amount of energy in the reactants and the products. Let's look closely at what happens when we burn that coal. Remember that the universe will be the chemical reaction and the surroundings. Jaden.
Wagwan.
Let's imagine that the coal and oxygen had this amount of energy before they reacted. Now, when they react together and the coal starts burning, where would you put the line for the product? Would it be higher, lower, or at the same level?
It gets hotter, so the products will have more energy.
What do you think, Tatiana?
Yeah, that makes sense. The line will be higher.
The line is actually lower.
Jesus Christ.
Don't feel too bad if you got it wrong. I used to think this way as well, but let me change your way of thinking about this to make this more intuitive for you. Imagine that this box is the system and everything outside of the box is the surrounding. The pink substance inside the box is representing the energy in the system, okay? This chemical energy is the energy in the coal and oxygen before they're reacted. So this is the energy in the reactants. Now, when the reactants turn into the products, the surroundings gain thermal energy and also light and heat energy. But let's just focus on the heat energy, okay? Remember that energy cannot be created or destroyed. This means that some of that energy that was locked up in the box, in the reactants, in the system, some of that energy has leaked out into the surroundings, making them feel warmer, because that energy didn't come out of nowhere, remember. The logic then follows that we have less energy in the system after the reactants have turned into the products. So the products have less energy. So just think about that again. Energy is not created or destroyed. The reactants had a set amount of energy, and some energy went into the surroundings afterwards. That energy didn't come out of nowhere. If your reaction is getting hotter, that means that your products have lost energy when they turn from the reactants to the products. This means that in reactions like combustion, anything that gets hotter, energy is released into the surroundings because the reactants have more energy than the products. That energy was released. We also have other reactions that don't feel warmer but actually feel cooler after they've reacted. These are what happens inside cold packs. If you've ever had an injury in a sport and they put a cold pack on you, this is the reaction that's happening inside. Now, if this is where the reactants are for this reaction happening in the cold pack, would the line for the products be higher, lower, or at the same level as the line for the reactants? Well, this is the opposite reaction to the previous reaction we were just looking at, so the line should be higher. And that is because the system is absorbing energy from the surroundings. Essentially, it's absorbing energy from your injury, trying to cool down your tissues around it, trying to cool down your blood vessels so they don't swell up too much. This means that energy inside your hand or inside the thermometer is being transferred into the system, which is why it feels cooler. Now, we have some special names for these reactions. One is endothermic and the other one is exothermic. The thermic part, most of you guys have probably clocked, is talking about thermal energy. It's talking about heat energy, okay? Endo means within or inside something. Exo means out or outside. Just like when we say insects have an exoskeleton, that's because they have their skeleton, the hard part of their bodies, on the outside, but ours is an endoskeleton inside our actual bodies. Now, I've got a relatively straightforward task for you now. Match up the definitions for exothermic and endothermic reactions. Well, they were already matched up. So, exothermic is the transfer of energy towards the surroundings, that is energy exiting, and endothermic reactions is absorbing energy from the surroundings. Okay?
Okay.
Before I move on to the concept of activation energy, spend some time identifying which of these is showing the endothermic reaction and which one is showing the exothermic reaction. In the reaction profile for A, and that's what these diagrams are called, they're called reaction profile. For example A, the reactants have more energy than the products. That means that energy has exited the system. This is an exothermic reaction. And the other one, the products have more energy than the reactants, so the energy has gone in from the surroundings. So that Next one is an endothermic reaction. Energy is entered. Now, which one of these will feel hot and which one will feel cold? The one where the products have less energy will be hotter because that energy has been released into the surroundings, which will include the thermometer or your hand. And the one where the products have more energy will feel cooler because it's taking energy from its surroundings, so from the thermometer, from the air, from the hand that's holding it, etc.
This is absolutely wonderful.
Thank you very much.
Alright, I've got coal in my pocket and oxygen in the air, but it doesn't start giving out thermal energy straight away. The chemical reaction hasn't started yet. We need to activate the reaction. Look carefully at this. Are we adding energy to the reaction or are we taking away energy from this reaction? We are adding energy to this reaction. This energy that we add to activate the reaction, oddly enough, is called the activation energy. This means that we have to add more things to our reaction profile. We need to show that initial input of energy where our reactants are. And so that should look like this. Notice that this is still an exothermic reaction. The products still have less energy than the reactants. Alright then, if this is the reaction profile for an exothermic reaction with its activation energy shown here, I would like you to just picture in your mind, or if you've got paper at hand, draw what an endothermic reaction profile would look like with the activation energy. Remember that the products should have more energy than the reactants, and you should also input that energy where the reactants are. The difference between where the reactants and the product is known as the overall energy change, okay? Notice the direction of the arrows. It is pointing from the reactant level to the product level. So it points down for exothermic because the energy is decreasing in the system, and it points up for endothermic because the energy is increasing in the system. The next label you need to accurately identify is the activation energy. This goes from the reactant level to the peak of your curve. The best way to do this is to draw some dashed line from where your reactance level is and then draw a vertical arrow pointing towards your peak. Before we go on to bond energies, let's answer a couple of past paper questions.
You're teasing me, you naughty.
The reaction between sodium and chlorine is exothermic. Complete the reaction profile for the reaction between sodium and chlorine. This is 2 marks. Do your thing. You get 1 mark for a curve that moves up and then down, and then your second mark comes from having the product line below the reactants. No long thing. Let's do one more.
Another one.
Figure 2 shows the reaction diagram, which is also the reaction profile, for a reaction between hydrogen and chlorine. And here we have the diagram. Tati, is this an exo or endothermic reaction?
The products are lower, so it's exothermic.
Now you lot at home, spend some time identifying the label A and B. What do they represent? The arrow that goes from the level of the reactants to the peak is always the activation energy. The arrow that points from the level of the reactants to the product level is the overall energy change. Alright, we're gonna move on to some of the higher paper stuff now. To deep bond energies, let's take a standard combustion reaction. Here I have 1 mole of methane reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. If you don't understand what the big and small numbers mean, check out my video on balancing equations. Anyway, if we look at the displayed formula for the reactants, we see that the atoms are bonded together by specific bonds. Methane has 4 hydrogens bonded to 1 carbon, and each oxygen is 2 oxygen atoms bonded together. Carbon dioxide is 1 carbon bonded to 2 oxygens, and each of the water is 1 oxygen bonded to 2 hydrogens. The oxygen and carbon dioxide actually have double bonds within them, but we don't need to worry about that right now. We'll look at that in a bit. For the atoms in the reactants to rearrange into the atoms in the products, how they're bonded, we have to break the bonds in the reactants and make the bonds in the product. Does that make sense? We basically are changing where the atoms are joined up with. In the left hand side, the carbon is joined with hydrogen, but on the right hand side we need it to join with the oxygen. So we're breaking the bonds on the left and we're making the bonds on the right. Okay, this top reaction is showing how bonds are broken, and the bottom one is showing how bonds are made. Now, answer these challenge questions. Bond breaking is absorbing energy from its surroundings, so it's endothermic. Bond breaking is releasing energy to the surroundings, so it's exothermic. And the type of energy here is thermal or heat energy. The calculations we're about to do are called bond dissociation energies, but for GCSE you can call them overall energy change. And this is the total of the bonds broken minus the total of the bonds made. I know that sounds like gibberish, so let's do a worked example together. And this is what that looks like.
Oh my god.
Stop complaining and just watch how I do this. Propane is a hydrocarbon fuel obtained from crude oil. Figure 2 shows the displayed equation for the complete combustion of propane. The table below shows the bond energies. Calculate the overall energy change in kilojoules per mole for the reaction. Use the diagram and the table above. Alright, so remember that the overall energy change is the bond broken minus the bond made. To work out the bonds broken, we have to add up the sum of the bonds on the left hand side of the equation, because remember, those have to break. We have carbon-carbon bonds here, and there's 2 lots of them.
1, 2.
So we have to break those 2 carbon-carbon bonds. The carbon-carbon bond has a bond dissociation energy of 347. So 2 times 347 gives us 694 kilojoules per mole. Kilojoules per mole is just the units. We have carbon-hydrogen bonds that we also need to break on the left-hand side, and we have 8 lots of them. And each of the carbon-hydrogen bond has a bond energy of 413. So 8 times 413 gives us 3,304 kilojoules per mole. And finally, we have oxygen-oxygen double bonds here. So now we're concerned about the double bonds. And we have 5 lots of them. That's because we have 1 double bond for each molecule of oxygen, but we have 5 molecules of oxygen, so we have to break 5 lots of it, okay? And the oxygen-oxygen double bond has an energy of 495. So 5 times 495 gives us 2,475 kilojoules per mole. Now all we have to do is sum these numbers up together. When we add all those numbers together, we get 6,473 kilojoules per mole of energy that we need to break the bonds in the reactants. And now we just do the same thing for the bonds being made. We have carbon-oxygen bonds on the right hand side, and there's 6 lots of them. 2 in each molecule, and we have 3 molecules each. So 2 times 3 gives us 6 bonds that need to be broken. The carbon-oxygen bond has a bond energy of 799. So 6 times 799 gives us 4,794. We have hydrogen-oxygen bonds here as well, and there's 8 lots of them. 2 in each molecule, and we have 4 molecules. So 2 times 4 gives us 8. The hydrogen-oxygen bond has a bond energy of 467, and so 8 times 467 gives us 3,736 kilojoules per mole. All of that added together gives us 8,530 kilojoules per mole. Therefore, breaking minus making gives us minus 2,057 kilojoules per mole. The minus tells us that energy has been released from the system to the surroundings. So the minus tells us that this is an exothermic reaction. If all of that was a bit too much, just skip and go back before you attempt this next one by yourself. So this is the one I'd like you to do all by yourself.
Oh my God.
This is from an A-level paper.
The man is killing us, man. Over.
Look, I know it's from an A-level paper, but their calculation is exactly the same, which is why I'm using this, okay? Just follow the same steps that we did. Remember that it's bond breaking minus bond making. We have carbon-carbon double bonds here, and there's just one of it. So each carbon-carbon double bond gives us bond energy of 614. 1 times 614 gives us 614 kilojoules per mole. We also have carbon-hydrogen bonds here, and we have 4 of them. And each one is 413. So 4 times 413 gives us 1,652 kilojoules per mole. Finally, a bromine bond here as well, and we've only got 1 of that. The bromine bond has a bond energy of 193 kilojoules per mole, so that is 193 kilojoules per mole. Summing all of that together gives us 2,459 kilojoules per mole for the bonds broken. And now for the bonds made. We have a carbon-carbon single bond here, and there's just 1 of them. And the carbon-carbon single bond has a bond dissociation energy of 348. So that's 348 kilojoules per mole. We also have a carbon-hydrogen bond, and we have 4 lots of them. And so 4 times 413 gives us 1,652 kilojoules per mole. And then we finally have the carbon and bromine bond, and there's 2 lots of them, and each one is 276. So timesing that by 2 gives us 552 kilojoules per mole. Summing all of that together and minusing what we have gives us a total of minus 93 kilojoules per mole. And there we go. Lesson is done.
Fatality.
This was the last episode of Chemistry 1. That means we've covered all the videos in the combined trilogy for Chemistry 1. I've made a playlist here that goes through all of the lessons and the required practicals for Chemistry 1 as well. We are gonna jump back to Biology 1 now, so check the description for all the goodies, and I'll catch you guys in a bit.